Hi, welcome to Lab Workshop 3 on linear programming. The first problem we're going to look at is the problem of heavenly hound kennels. They provide logic for pets. The kennel's dog food. They make their own dog food by mixing 3 grain products. So Doug, the manager of Heavenly Hound Kennels, wants to make sure that each dog consumes at least 225 grams of protein, at least 30 grams of carbohydrate, and no more than 15 grams of fat each day. And we're given the cost of each of the 3 grain products, the dollars per kilogram, and we're given the percent protein, percent carbohydrate, and percent fat. We're asked how much of each grain product should each dog be fed in order to minimize Doug's costs. So this should sound like a blending problem to you. And blending problems are one of the types of problems we can use linear programming for. So with linear programming, first thing we're going to do, we'll put a title up here. So this is Heavenly Hound Kennels. And we set up our Excel spreadsheet in 3 different sections. So the first section is called Model Parameters. And this is where we're going to put all of the data that we've been given. With model parameters, we generally have columns for each of our decision variables. So this is a blending problem. We have 3 different grains, grain A, grain B, and grain C, that we want to mix into this dog food. So we're going to have a decision variable associated with each of those. We want to know how much grain A should we put in the mix, how much grain B, and how much grain C. So those are going to be our decision variables. So I'll put A, B, and C here as headings for my columns in model parameters. And then the first thing I usually want to put is the coefficients for my objective function. So my objective function, I'm going to try and maximize or minimize Z, which is equal to a linear function that involves my decision variables. So my objective function, or here, my objective function coefficients are going to be the cost. I'm going to be trying to minimize cost. So I'll put cost. It's always good to put units, keep track of your units. So this is dollars per kilogram. And we're told that grain A costs $4.50, so 4.5. Grain B costs $4, and grain C costs $2.70, or 2.7. So that's our cost per kilogram. We have 3 constraints in this problem. We need the dog food mix has to have at least 225 grams of protein, at least 30 grams of carbohydrate, and no more than 15 grams of fat. So we're going to have a protein constraint in terms of percentage. We're going to have a carbohydrate, we'll just say carb constraint, and a fat constraint. For proteins, as far as protein goes, for every kilogram of grain A that we give a dog, the dog gets 0.62 kilograms of protein. So our coefficient here is 0.62. For every kilogram of grain B, the dog gets 0.55 kilograms of protein, and for every kilogram of grain C, the dog gets 0.36 kilograms of protein. So those are our coefficients for the protein constraint. And then in model parameters, the other column we need up here is the limit. For each of our constraints, there's a right-hand side which gives us the limit. So in this case, we were told that protein should be at least 225 grams. Now we do have to be worried about our units here because our costs are in dollars per kilogram. So I want to put the limit in as far as in terms of kilograms as well instead of grams. So 225 grams is equal to 0.225 kilograms. For carbs, we get our coefficients for the carbohydrate constraint. So for grain A, it's 0.05. For grain B, it's 0.1. For grain C, it's 0.2. And our limit here was 30 grams of carbohydrate, so that's 0.030 kilograms. And then fat, our coefficients, the percent fat in each grain, for grain A is 0.03, for grain B is 0.02, and for grain C is 0.01. And our limit for fat is 10 grams, so 0.010 kilograms. So that's our model parameters. Sorry, I just have to fix our limit. There was 15 grams of fat, so 0.15. 0.015 kilograms of fat is our limit. Now the second section that we set up in our spreadsheet for linear programming is our decision variables. So I'm going to put some labels here. So I'm going to call this XA, XB, and XC. So that's what I'm going to call my decision variables. But what's really important is the 3 cells underneath those labels, because those are just labels. So it's often a good idea to color those cells or put borders around them, just so you remember that that's where your solution is going to appear. And now the last section that we do is our model output. And this is where we build our mathematical model. This is where we put in all the mathematical relationships between our variables. So in general, we have 3 columns here. We have value, right-hand side that we'll use for our constraints, and then a slack/surplus column. And the very first thing we set in our model output is our objective function. And in under the value column there, we're going to put the linear function that describes our objective function. So our objective function is our cost coefficients times our decision variables. It's a sum product. So this is going to be equal to sum product of our cost coefficients, comma, and our decision variables. And right now it's 0 because there is no values for our decision variables. And then we're going to put our constraints. We want them in the same order as we have them up here, so I can copy those, bring them down here. I usually like to set out whether it's a maximum or a minimum. So this is a protein minimum. We were given a carb minimum, and we were given a maximum amount of fat. So the left-hand side of my constraint coefficient for protein is going to be a linear function of the coefficients for my protein constraint and my decision variables. So that's so again, that's just the sum product equals sum product of my protein coefficients, comma, and my decision variables. And you can see a pattern here. In fact, we can actually go to our objective function. If we set up everything properly in the model parameters section, my sum product in my objective function, where I'm pointing to the decision variables, I can just make that an absolute reference. And then I can really take that function and copy it down for the rest of the constraints. For the constraints, I also have to put the right-hand side, and that's equal to my limits. So for the right-hand side for protein, I'm going to say equals and go and show it where the limit is. And again, with relative references, I can copy that and paste it down. And then slash surplus is just equal to the difference between the right-hand side column and the value. So right-hand side column minus value. And I can take that and copy that formula and copy it down. So now I've got everything in here to solve my problem. So I can go to Solver. So I go to the Data tab at the top and choose the Solver, Add in. And it says set my objective. So it wants to know where my objective function is. So I show it where my objective function is. I show it the cell that has my objective function. In this case, we're setting it to a minimum. We want to minimize the cost. So I'll click the minimum button. And then by changing my variable cells. So my variable cells are these cells right here under those labels. So Excel is going to try different numbers in those cells until it finds a minimum value for my objective function. And then I have to tell it my constraints. So I add constraints. For each constraint, I put in the left-hand side and the correct inequality sign. So in this case, I want the protein value to be greater than or equal to 0.225. I can add it. I want the carb minimum to be greater than or equal to the right-hand side of that constraint, and I'll add. And then I want the fat maximum to be, the fat amount to be less than or equal to the right-hand side of that constraint. When I'm finished putting constraints in, I say OK. And I'm back to my main solver screen here. As mentioned in the lecture, solver takes care of the non-negativity constraints so long as this box is checked. So we want that box checked. And then we need to select a solving method. And we're using simplex LP. So LP for linear programming. So everything should be set. We'll say solve. And it tells us that solver found a solution. All constraints and optimality conditions are satisfied. It asks us if we want to keep the solver solution. So we take a look at it, and it looks okay. Before we answer that, we can sort of look at a few things here. So it's telling us that we should be adding 0.174 kilograms of grain A and 0.213 kilograms of grain B, and no grain C. If we do that, our objective function, the value for my objective function here, so that's my cost. I was trying to minimize the cost, so with that particular mix, my cost is $1.63 per dog per day. I'm getting exactly the minimum amount of protein. I'm getting exactly the minimum amount of carbs. And with fat, I was allowed 0.015 kilograms or 15 grams of fat. I'm actually only getting 9.5 grams of fat. So everything looks okay. I can keep the solver solution. One other question, so we've answered what's the total daily cost of food for each dog. The worksheet says to request a sensitivity report. So there are some other reports we can ask for here. I will ask a sensitivity report. We'll talk about that in the lecture, but they'll just show you how to ask for it. We'll say okay. And so our sensitivity report is actually added as a new worksheet down here. That's what it looks like. And like I say, we'll talk about it more in the lecture. So this sheet is Heavenly Hound. And that's our linear program. Part D, I did ask you to do a try at home. This is another example of an additional constraint. So if we had said that, if we looked at the solution and said, well, there are other minerals and other nutrients in each of these grains, so I'd rather make sure that the dogs get a good variety of grains. So I'd like to force the solution to include some of grain C. So I could do that by putting an additional constraint that says that each grain must make up at least 10% of the protein part of a dog's diet.